Today I am going to be talking about update strategies for edge devices. This can actually be like a deceptively difficult problem to solve for, especially if you're dealing with a fleet of devices with different capabilities. So, if you're dealing with a fleet of devices with a ton of different capabilities, it can be really difficult to solve this problem. More difficult than you would expect because it's a computer, right? So it should be easy to develop for if you might think that if you're not like deeply involved in the embedded space. But there are some tools and design strategies that we can implement that make this a little bit easier on everybody. So, about me first, my name is Kat Cosgrove, and up until the last year or so, I was actually an engineer at JFrog on the IoT team. And we built a really, really flashy demo involving a car to try to prove that over the air updates for edge devices didn't have to be as difficult as they are right now. Our ultimate goal was to try to bring DevOps to the edge. It's still a space where it's less of a thing. And in the course of trying to solve this problem, we came across some really interesting tools and solutions that we could bring into a CI/CD pipeline for embedded Linux devices. And the demo I'm going to talk about is the one that Victor saw. We love talking about the ins and outs of that demo because it was harder than it looked. Let's see. Just a quick overview of the agenda because these talks are long. In part one, I'm going to go over like the actual technical details of what we did and the problem we were trying to solve. In part two, it's a little bit more fun. I'm going to be talking about the interactive part of the demo and how you can build the exact same thing at home for fun to harass your coworkers, your spouse, your roommate, your pets. It's fun. But first, we need a little bit of context. How large is the edge? Pretty big, actually. If you count both dumb sensor edge devices and smarter ones like gateways and things like phones, I guess, count as edge devices these days, it's an estimated 20.4 billion devices. It's a lot. So, how are they being updated now? A lot of them don't. Some of them just can't be updated. They're throwaway devices, effectively single use. When they break, they just need to be replaced. And a lot of the devices that can be updated do it in a way that's sort of unwieldy. It's time consuming, or the infrastructure to support it is really complicated, or it can't be done wirelessly at all and needs to be plugged into a computer. It requires physical access, which is either annoying for the user or costly for the company because they have to pay an engineer to go out there and update it. This is particularly a problem in industrial IoT. But in spite of that, the industry is huge. It's booming. It's getting bigger and bigger and bigger, and we're making more and more money off of it. So why is this a problem that we need to change? It's more than just a little bit inconvenient, actually. Our lives are increasingly reliant on edge computing and IoT, with devices taking over larger and larger workloads in the consumer, industrial, medical, retail, every vertical you can imagine. IoT and edge computing is taking up huge amounts of work. And people don't want to spend lengthy amounts of time waiting for a software update to complete. And they definitely don't want to have to plug a device into a computer to do it, especially when it's, rapidly becoming most of our lives. It's also really dangerous. We all know that infrequent or non existent software updates are a huge security problem in anybody's network, regardless of the reason for it. And it could mean anything from the exposure of user client data to a malicious third party to devices being harnessed for a botnet or cryptocurrency mining. This has already happened on a wide scale. It's continuing to happen today. A bunch of people's smart appliances, like smart refrigerators from Samsung and companies like it, got harnessed to be used as part of a botnet executing DDoS attacks just like a year and a half ago. It's absolutely a problem. Okay, it's an issue. Why aren't we fixing it? What is slowing us down here? A lot of devices are just not designed with the ability to be updated. Even if the manufacturer wanted to patch a security flaw, they couldn't. They expect to run the software version they ship with until they break, and the update strategy for these devices is just flashing them. That's not an update strategy. That sucks, because how often do you write perfect code? I know we all want to think that we're like totally flawless, genius 10x engineers, but how confident are you really that there's not a single bug in your code and that your QA team is going to catch every weird edge case you can imagine? You should not be that confident. On average, there are between 1 and 25 bugs per 1,000 lines of code. Bugs are making it into production. You can't gamble on your code being perfect. I tried to phrase this in a way that made it clear just how commonly bugs exist in software, whether you know they're there or not. And lines of code was as concise as I could get it. But think of how long the average application you write is across files, probably more than 1,000 lines of code. That's a lot of bugs. We also have some connectivity concerns we have to deal with. The device's network is unreliable. Networks hosting edge devices are often unstable. The connection might be intermittent. Connections in general are often unstable. The speed of the network might be really, really slow. So we need to keep the updates as small as we possibly can. And the network probably isn't secure either. So the updates need to be signed in some way so that we know that they're trustworthy. Those 20.4 billion devices are also not running on any kind of standardized hardware. Each class of device has something specialized. It's not predictable, with differences in available communication protocols, memory, storage space, operating system sophistication, and on and on and on. So, how do we design a system that takes all of these differences into account, handles them, and allows us for easier deployment to broader classes of devices instead of just a single board or device type? Is it possible to get a like one size fits all solution in an industry that comes in like a lot of different sizes? Probably not. We probably can't get one size fits all, but we can get something one size fits a lot. We can build something flexible that will take minimal effort to shift over to a different device type. But first, we have to start thinking about the future. We have to stop building these devices that can't be updated. Throwaway devices are not acceptable anymore. Besides the glaring security problem and having a fleet of devices out there that can't be patched if a security flaw is found, like imagine if that CVE from F5 from over the weekend was unpatchable. It would be a disaster. So we have to stop for the security reasons alone, but also the ecological impact of continuing to design these throwaway devices is totally unacceptable. All 5,000 of the medals made for the Tokyo Olympics were made from metal harvested from discarded electronics donated by the people of Japan. That is an absolutely staggering amount of tech trash. 5,000 Olympic medals from harvested electronics. Bonkers. Design with the philosophy that your device, your product, should get better with age. it should improve over the course of its usable lifespan. The key word is usable lifespan here. I'm not asking you to design a device that never needs to be replaced. That doesn't make sense from a business perspective. And anyway, hardware becomes obsolete. But I am asking you to design something and release updates for it for like, 3 or 4 years. Not forever, but until the hardware is obsolete. Your product should not be getting worse from the moment you ship it. That's sad. And build more robustly. A bad update should never brick the device. There needs to be a way to roll back immediately and automatically if something goes wrong. Otherwise, your updates aren't trustworthy and your device is brittle. And use modern DevOps tools. There are a lot of moving parts in pushing an update to the edge, and it's much easier to manage if you have a robust CI/CD pipeline in place. Do your engineers a favor. Don't make them handle any of this manually if they don't have to. So the proof of concept. To drive this point home, we built a proof of concept using the most tangible example of an edge device we could think of, a car. Not a real one. Obviously, JFrog wouldn't buy us a real car to potentially brick. That's too expensive. We built our own, and I will talk about that in the last half of the talk. So, how do cars get updated now? The overwhelming majority of cars can't receive software updates over the air. They need to be brought into a service center to do it. I know some of you thinking, oh, Tesla. Yes, Tesla can receive over-the-air updates, and like one or two other car manufacturers can as well for some systems, but that's not the norm in the automotive industry by any stretch of the imagination. Cars that can be updated over the air, some of them still take quite a while to do it, and you can't drive the car while the update is happening. Different cars are also still using different boards and running on different operating systems. So even in one corner of the market, there isn't really any standardization on what's going on under the hood, so to speak. And 15%-ish of vehicle recalls are actually the result of bad software. Famously, Jaguar had to issue a recall to fix an issue with the braking system in one of its very, very expensive SUVs. Required a trip to a service center for 8 hours to reflash the computer. Also, another car in, I think it was Hong Kong, stranded its owner on the highway with the doors locked because although this car could receive over-the-air updates, it couldn't roll back a bad one. So you got halfway there, but now you're trapped on the highway and you can't open your doors. So this is a very real, very painful, and very potentially dangerous issue that presented us a range of solvable pain points for both the end user and the manufacturer. And the combination of all these issues in one single device made it a great example for proving that we don't have to do things this way anymore. Because we were working with a car, not a real one, we were very motivated to make this update happen quickly, reliably, and without the potential for injury to the user. Because a failure in this case, when you're dealing with, a couple thousand pounds of moving metal, could be fatal. So to simulate the car, imagine a Raspberry Pi 3B Plus running automotive grade Linux. Automotive grade Linux is a real thing. Car manufacturers are starting to move towards using it. Thankfully, it's very cool. So let's talk about the two workflows we had to make this work. We had two completely distinct workflows here. For one, we updated software running on the car without flashing the firmware. This didn't interrupt the user at all, took only a few seconds, and relied mostly on K3S and Helm. We also had a workflow for firmware updates. This one was a little bit more difficult, a little bit more complicated. It still only takes a few minutes and doesn't really interrupt the user either. It's got an automatic rollback if there's any kind of failure, and this one relied heavily on Mender and Yocto. We'll go into the software workflow first. This is just a quick overview of the technologies at play in a workflow for software updates on the device. We used Artifactory to manage and store all of our various build artifacts, as well as handle promoting builds from dev to production to tell us it was time to deploy. X-ray is used to scan our package dependencies before release to make sure that there's nothing sketchy going on in our supply chain. And K3S and Helm are used to actually deploy to the car. You can use whatever CI tool you want here. We used one during development and another during the actual demo. I think during development, we actually used BuildBot, and during the live demo, we used pipelines. First up is K3S with the absolute cutest slogan in open source, Kubernetes, but 5 less. K3S is just super lightweight Kubernetes designed for edge devices. It uses only 512 megabytes of RAM. It produces a binary of just 40 megabytes, and it has very, very minimal OS requirements. The packages required dependencies are just containerd, flannel, core DNS, CNI, and some utilities like IP tables and SOCAT. It's wrapped in a launcher that abstracts away some of the complex issues with Kubernetes, like generating TLS certificates and setting various options. Kubernetes has a reputation for being really hard, for being very complicated. K3S is still difficult, but considerably easier than entire Kubernetes. Next up is Helm. If you work with Kubernetes already, you are probably familiar with Helm, but just for anybody in the space who isn't super familiar with it, it uses charts. It describes your application, and it allows you to have an easily repeatable and predictable installation. The charts serve as the final authority on what your application will look like, and they're super easy to version, and it also supports automatic rollbacks in case something goes wrong. This is part of one of the Helm charts for this demo. It's building the microservice we were using to allow us to control the miniature car with a race wheel designed for video games. The syntax here is fairly simple. It's just YAML. DevOps runs on YAML. So if we can put YAML in it, we will. The result of using those two tools is that application updates are quick and very efficient. We've got an average of 35 seconds from a developer pushing code to deployment on the car with zero interruption to the user. This can happen while the car is in use, while it's actively being driven, which is what we demonstrated live. That's not to say that it necessarily should. In the case of an actual car, there should be consent involved. You should at least inform the user that this is happening. But if you design your edge device with this strategy in mind, you absolutely could update silently with zero indication that something has happened. I think this is a pretty compelling setup for things like industrial HVAC setups, where probably you don't ever need to interact with it unless something is physically wrong. Let's take a look at the slightly more complicated firmware workflow. Similar to the software workflow, this is just an overview of what's going on in our system. Yocto is used to create our builds. We have some CI tool, in this case pipelines, handling all of our events again, X-ray checking our packages for vulnerabilities again, but we're using Artifactory for a little bit more than before. It's going to be handling some of the workload for Yocto, which will speed things up considerably, and Mender is being used to handle our over-the-air deployment. Let's talk about Mender first because it's the coolest over-the-air updates for embedded Linux devices. So Mender ticks several of the boxes we're looking for. The updates are cryptographically signed and verified. It supports automatic rollbacks if something goes wrong, and it allows for several distinct installation strategies, but the one we're going to be focusing on is the dual AB strategy. Using this method, two partitions exist on the device, A and B. The bootloader is aware of which partition is currently designated as active and which is not. It boots into the one designated as active, obviously. During an update, though, the inactive partition is updated with the new firmware. It streams directly there in the background. The user doesn't know. At this point, the partition running the update is designated as active, and on reboot, the bootloader switches into the newly updated partition. But because the old partition with the previous version still exists, if something goes wrong, it won't boot, it doesn't behave correctly, it can automatically roll back to the old partition and reboot there. So, for example, you get in your car, you're going to go to the grocery store, and you turn on the car and it says, hey, a new update's available, do you want it? And you say, yeah, sure. And then you keep driving to the grocery store. While you're driving to the grocery store, the update streams in the background to the inactive partition. You park your car, you do your shopping, you come back out, start your car, and the partition's flipped. And you're on the new version with zero interruption. You told it you wanted it, and it happened. And so the only perceived downtime for the user here is a reboot, which is pretty low effort with a car. But we still have a problem with the size of our builds. It's happening silently now. It doesn't interrupt the user, but the build might still be pretty big. So it might not be able to happen in 10 or 15 minutes or 5 minutes or whatever. Let's see if we can get them a little bit smaller. Enter the Yocto project. It's custom Linux distributions for any hardware architecture. Yocto works by reducing the resources used on the board and minimizes hardware requirements by building a distribution specific to the modules you need for your particular hardware and your particular scenario. So if you know that your device is only ever going to need to communicate over Bluetooth, you can build a custom distribution that doesn't include modules for Ethernet and Wi-Fi. Just not there to begin with. It's really, really, really convenient. It uses bitbake syntax to write recipes for your build, pulling in layers for different hardware configurations and applications. We used a layer for the board itself, like I said, a Raspberry Pi 3B, as well as layers for K3S and Mender. There's a pretty large community around Yocto, so a lot of things you want might already exist for it. It's also possible to write a custom layer to isolate specific applications or behaviors if you want to. This is an example of the meta layer that adds K3S to our Yocto build. The syntax is pretty straightforward. It allows for the execution of both Python and shell scripts in parallel. You don't have to be an expert in either of those technologies to read and write this. Any engineer should be able to do it pretty quickly and easily. The first build will take a while, no matter what. We're building an entire operating system, so there's not really a way around the first one being time consuming, but we can speed things up drastically for future builds. Yocto caches everything it downloads during a build, which allows for incremental updates. If you have it use this build cache, then it'll only rebuild what's changed. So this is where Artifactory comes into play. We used a generic repository to store the Yocto build cache and directed Yocto at that so that it would use it during subsequent builds. For us, this reduced the time required to rebuild by as much as 50%. It's a pretty significant difference. So the result is that using Mender to handle our over-the-air deployments and Yocto for our builds, when we were pulling the build cache from Artifactory, is that the time for a full firmware update was between 5 and 10 minutes after the first build. the build is as small as we can get it, minimizing potential issues with low bandwidth or issues on the device's network. The updates are signed, satisfying the security requirement, and automatic rollbacks are in place in case of something going wrong. So we succeeded here too. There are some other tools that didn't make it into our proof of concept, but are still very much worth mentioning in the context of embedded Linux development. First is OS tree, which you may be familiar with. It's just Git for operating systems, basically. It uses a content addressed object store with branches to track meaningful file changes. It can be used to update a system even incrementally, and also supports rollbacks like we need it. There is a Yocto meta layer for this that allows for over-the-air updates using OS tree and actualizer. It's already used by a few different Linux distributions for updates. There is no real reason we went with Mender over OS tree, aside from we found Mender first and we were already working. Then there's Lava. This is one of my favorite tools. It's a testing framework for operating systems on embedded devices. It stands for Linaro Automation and Validation Architecture, and it is a CI system for deploying an OS to a device for testing. It can deploy to either physical or virtual hardware, up to you, and it can handle simple boot testing, bootloader testing, or more complicated system testing with results tracked over time for further analysis. We have this set up in the IoT lab at our office in Seattle. So it was designed for validation during development, testing whether the code that engineers are producing works in whatever sense that means for your particular context, detecting whether changes in the Linux kernel compile and boot, or whether the code produced by GCC is smaller or faster. It is outstanding at device management, though. Like the testing part is cool, but what it's really good at is device management. It's got templates in place for more than 100 boards built in. And you can add custom devices if you want. It is difficult to do. I won't lie. The learning curve with Lava is pretty steep, but you can integrate an unknown device if you want. This is just an example of a device overview showing a SOCA 9. Yeah, a SOCA 9 and a HiKey 960, both with a health status of good. So they've been passing their regular health checks. And no manual tests have failed recently, it looks like. Below, at the bottom picture, we have the detailed results of an OS test on the SOCA 9, showing each test defined and its results. Linaro actually maintains a validation laboratory in Cambridge that's publicly accessible, which is where this screenshot comes from. So you can just play with an already set up version of Lava, or at least poke around before you try to set it up yourself. So wrapping up the first half, the way a lot of edge and IoT devices are being updated now, if at all, is super broken. It is a gigantic security flaw that really, really needs to be addressed, and it does not have to be this way anymore. We have technology available now that handles some of these problems for us. We just have to use it. For edge devices running embedded Linux, a modern DevOps pipeline, and a handful of open source tools can make it almost as easy to deploy updates and security patches to your edge devices as it is to any other application. If you only need to update applications running on your device, K3s and Helm can make things very quick and easy. I know Kubernetes has a pretty steep learning curve, but K3s is simpler to use, I promise, for anybody in the crowd who has not actually used a ton of Kubernetes. If you need to update the device's firmware itself, strongly consider Yocto and either Mender or OS tree. They have different design philosophies, but they will both get the job done, and they're both fantastic tools. Definitely have Yocto store the build cache somewhere and actually use it. There's no reason not to. just makes your life easier. And if you have a need for testing your update against a wide variety of boards, Lava is absolutely the best option to look at in my opinion. The learning curve with Lava is also fairly steep, but their documentation is very large, and also they're very, very active on their mailing list. So if you have a question, just hit the mailing list and somebody will answer it. Maybe me, because I'm also on that mailing list. So let's move on to part 2, the fun part of the story. Welcome to the second half, snakes on a car or over-engineering a toy. There is not usually room in my talks for me to talk about my favorite thing about this demo, which is building a miniature self-driving car. Usually I have to give this talk in like 30 or 40 minutes, so I don't have time for this part. So this is exciting. So like I said earlier, for JFrog's user conference last summer, we built a proof of concept demonstrating over-the-air updates for a car. We used a car as our example because it is flashy, and it's not something that a lot of us think of as an IoT or an edge device, even though it totally is. There are 3 or 4 computers in modern cars, at least. And since JFrog wouldn't buy us a real car, we had to build our own, inspired by a hackathon I had run a few months earlier. From a technical perspective, it was still really cool. And you can build one of these too. They're not that difficult to build. They're not that expensive. We made some modifications to ours, which is what I'm going to be talking about. What I didn't mention about the demo earlier, and thankfully Victor didn't mention it either when he introduced me, is that we actually let people play with the demo. This wasn't something that was just static and in a booth that we talked about. It was interactive. It looked really cool. We had a racing simulator set up in the middle of a large track, complete with pedals, a race wheel, a screen for the driver, a racing simulator chair, and a green screen around the perimeter of the track. That is me making sure everything works before the conference opens for the first day. I do not recommend trying to use a laptop and drive at the same time, however. We allowed people to interact with it in one of 2 ways. As a developer writing and pushing code to the car, we actually let real random people off the conference center floor that we did not know write code and push it to the car. We were very confident. Or you could drive the car while someone else updated it. And what we found is that mostly developers wanted to drive the car, and somebody from like biz dev or marketing wanted to be the developer for a day. And usually they wanted to push destructive updates. They wanted to push something that would mess with their coworker, which was always super fun to watch. And while this part of the demo wasn't as like revolutionary from a technical standpoint, it was really cool. It was really fun to build and still fairly complicated. It's a great way to dip your toes into hardware if you're not already a hardware engineer, and several other technologies. There was actually a lot going on here. This part of the demo was largely my baby, and here's how I did it. So we've got a basic self-driving miniature car, and I went to the office and grabbed one so that I could have it on camera. This is what it actually looks like. The demo actually began its life as a donkey car. If you aren't familiar with those, I certainly was not before I heard about them at a Python meetup. It's a miniature RC car that's been modified with a Raspberry Pi and a camera. The library that enables it to do its thing is called Donkey, hence Donkey Car. And they only cost about $250 to build for the most basic one. Once everything is set up, you record 10 or so laps on a track with anything high contrast. Honestly, you can just use like masking tape on the floor. Then move the images and steering data back to your car, use the Donkey CLI to train the model, and then move the model back and forth. So there is a manual process involved, since you have to jump from your car to the computer to the car again. But it's still fairly easy. The standard camera is just a regular Raspberry Pi cam, but people do modify these for racing. There's a whole community around like building, modifying, and racing these. People do upgrade them with like LiDAR cameras for better depth perception, or a second camera to give it stereo vision, bigger batteries, better tires, etc. Ours is just a little bit beefier than the standard donkey car. So the only difference between ours and what you build if you're doing the basic one is that we knew ours was going to need to do a little bit more work. So it's not just a Raspberry Pi 3B Plus, actually. It's a Raspberry Pi, it's got a compute module board on it. We needed the extra juice for some of the additional workload we were having it handle. But otherwise, this is something that you can totally build and mess with on your own. By default, you control it with your phone, but we changed that as well, which I will talk about. All right, let's go back to the presentation. So I'm kind of extra. And we wanted a setup where the person participating in the demo as the driver actually felt like they were playing a racing game or something. We didn't want it to be just like standing there at a laptop or, hey, go to this URL on your phone or whatever. We needed it to be like immersive. So this meant we needed to be able to control the steering with an actual wheel and the throttle and brakes with actual pedals. So we would have to modify the donkey library to make that work. We didn't want to mess with manually dumping the images and steering data during a live demo either. So let's automate that and move the model training up to GCP. I also wanted a TV screen in front of the driver's seat so they could actually use the car's camera to see where they were going. Otherwise, it's going to be like kind of disorienting to try to drive it. And since things aren't already complicated enough, let's throw a green screen around the track and learn some computer vision. So the standard donkey car is easiest to control with the web app it comes with on your phone. It's not very interactive, and it didn't give us the driving experience we wanted. So we needed to change that. The library calls its various moving pieces parts, and there actually is some documentation on adding new ones. This is supported behavior in the donkey library. It's not super well documented, but it is a thing that they encourage you to do. It also already had experimental support for a number of different physical controllers. These have been fleshed out more since then, but it didn't have one for a race wheel that worked with our particular race wheel. We had a Logitech G29. I think the one that it already supported was like a year or two older than that. So we just wrote our own. The race wheel part requires ZMQ and PyZMQ. It works by requesting the current values from the race wheel and the pedals via ZMQ proxy running on the machine the race wheel is plugged into. In our case, we had an Intel NUC tucked under the driver's seat. Actually, a whole lot of this demo ran because of that ZMQ proxy. We passed a lot of data through it. Once the part is added, swapping out the standard library is really, really, really easy. You just SSH into the Raspberry Pi, open up manage.py, and swap out the controller part. It should just be joystick controller by default. And in our case, we changed it to wheel. But that's all that's going on in the race wheel. It's just passing data, intercepting what it normally wants to do. But to make the driving experience feel a little bit more like an actual car, we needed to do some like pre-processing on the values from the race wheel before they got sent to the car. The standard library does not really account for things like throttle scale or steering veer. So we had these two helper functions to do some math for us before sending values over to the car. Otherwise, the throttle feels like really, really awkward and touchy. It doesn't super easily support braking. And the steering is kind of jerky We did also allow for customization of the force feedback on the race wheel to make it feel like looser or tighter, easier or harder to turn. Without this, driving the car using the wheel and pedals is totally still possible. It's just awkward and unintuitive compared to the way that you would actually drive a car. So it was a fairly easy improvement in behavior to make. The track is circular, so the driver needs a way to see what's going on, when to turn, and how to turn the wheel, especially if the car is behind them. To accommodate this, the knuck under the driver's seat is going to need to do a little bit more work. What we ended up with is a Sanic web server doing most of the work, and a Vue.js app for the front end. I will not show the code for the Vue.js app on the front end because it is some of the ugliest code I have ever written in my life, and it was never meant to see the light of day. And it won't see the light of day. Sorry. But instead of storing all the training data in a directory on the Pi, we are rerouting each frame and the accompanying steering data through the ZMQ proxy under another topic. An async function is subscribing to that topic, as well as a few other things, doing work for our CI/CD pipeline, the race wheel data, and some other things required for updates. And according to whatever current customization is defined in the configuration file we were letting users mess with, processes the data accordingly. At the bare minimum, the Vue.js app on the driver screen is displaying the raw camera data from the car, the current build number, and buttons to record or update new training data. Most people did drive the car manually most of the time, but some people were just super interested in the self-driving aspect and wanted to record a few laps and see if they degraded the model or not. Most people did degrade the model a little bit, but that's okay. So again, the Vue.js app is ugly. You can't have the code for it, but it worked by using JavaScript OpenCV bindings, which is a thing that exists. Didn't know there were JavaScript bindings for OpenCV before I went to do this, and an open WebSocket to just continually redraw the images from the camera topic to a canvas element. So at this point, the demo functions from an interactive standpoint, but it doesn't really look as cool as we want it to. People don't have any nice scenery to look at. So let's stand a bunch of green poster board up around the track and write a green screen. So in its simplest form, if you don't know anything about computer vision, a script like this works by using OpenCV to read in a frame, convert it from RGB to HSV, it's hue, saturation, and value, create a mask out of any parts of the image that fall within another range of HSV values that we define. And then you use that mask to like crop the background image you want and replace the corresponding spaces in your original image. To get closer to perfect, you can do some things like blurring, dilating, eroding to kind of refine the edge. We did a little bit of that here, and there is a little bit of guesswork involved in it too, with finding the right high and low ends of the HSV range you want to use, since things like lighting affect what color it appears to the camera. So it worked one way in our office, but once we actually got it to the conference center, we had to like dial this in again. But then you just convert it back to RGB and return the frame. I didn't know anything about computer vision before I embarked on this, so this was a whole learning experience for me. Some of this code is also probably a little bit ugly, but hey, we had 3 months to build this. It was very much a make it work, not make it pretty kind of situation. We've all been there. So our green screen needs to simulate scenery on a drive, though. So we could not just leave it static. The image had to appear as if you're driving past it. Otherwise, it's actually really, really disorienting. And we found that people would often accidentally just drive straight into the wall after the curve of the track. I did it myself a few times, and I like even being actively aware of it and trying not to be distracted, it was still a problem. So we got to figure out how to make the image move or look like it's moving. To do that, we use the current angle of the steering wheel and the starting X and Y coordinates to calculate how far we needed to move the area to crop for the background from one frame to the next. We also used a scale variable that people could mess with to increase or decrease the speed of the pan and make it feel like you were driving faster or slower. We did also allow for things like image filters and different backgrounds to be applied. Uh, those were just some of the updates we let the random people off of the conference center floor apply, things like going from the desert to the countryside or outer space. We also let people actively mess with the driver by flipping the screen upside down or whatever, which was a very, very popular option. But all of these used functions and methods that are already built into OpenCV, so there was no real magic there. So we also need to automate the training. This was actually relatively low effort once we got over some hurdles related to TensorFlow on GCP. Even though TensorFlow on GCP is allegedly well documented and explicitly supported, it was more trouble than we expected. Since we were getting the images and corresponding steering data from the car via our ZMQ proxy, we were able to pass that data along to a tub writer utility, also running on the NUC under the seat that is responsible for most of the demo, and then pass it up to GCP to train the model there. So whenever a new model was available, the driver's UI would update to reflect that availability and allow the user to select that on screen instead and let it drive around the track. This was still pretty slow, actually, up to like 10 minutes, but it's still faster and easier than stopping the car, manually moving the data over, waiting for the model to train on a laptop, and then moving the model back to the car. Because the car, if we can switch back to the camera view, is not very easy to get at in most cases. During the demo, it has a cover on it so that it like looks prettier. So every time when we were testing this, we would have to stop the car, take the cover off, and then usually there are two batteries. There's one here that's powering the Raspberry Pi and one here that's powering the car's actual like motor. To get at these tiny little micro USB ports, just to pull the data off the car and then train the model for longer than 10 minutes on a MacBook and then move it back. It was a huge interruption to workflow. And even though we did have 3 of these cars at the demo, it was still more work than we were willing to deal with live. So all of the effort we spent fighting with GCP to get TensorFlow to run up there was worth it to not have to fight with this little car multiple times a day, because an interaction in the booth would take maybe, I don't know, 10 minutes before people wanted to move on. And there was basically no downtime between the next person. We had a line the whole time. So it's just not feasible. I also want to mention something that did not make it into the demo but that is really cool and I'm super proud of. I'm sad that this didn't make it into the demo, but originally we wanted to track the car's improvement over time, driving itself, based on conference attendees and chart the improvement or failure of the of the driving. The way we planned to do that was with a camera on the ceiling and just image recognition. Look at the car, follow the car, track how often it deviates from the median. It turns out that that was more difficult than expected with all of the potential noise and interference and unpredictability of being in a conference center. And, like, most importantly, people wandering around. We didn't really have the time to train a super sophisticated model there. So what I ended up with was a Raspberry Pi taped to the ceiling with a Raspberry Pi Noir camera. Raspberry Pi actually makes an infrared camera. We then put an infrared LED on the back of this support strut for the camera. And we wanted to have the camera just watch that infrared LED. The Raspberry Pi Noir camera, however, can also see visible light. So we ended up with the same problem of distractions, too much going on. It turns out that while infrared filters for Raspberry Pi cameras don't exist, a floppy disk is an infrared filter. So you can just cut open a floppy disk, if you can still get one. I mean, you have to order them online. But if you just cut open a floppy disk and tape it over an infrared camera, that's an IR filter. And now that camera can only see infrared light. So we went from super distracting, would have to actually spend the time to train like a more sophisticated image recognition and tracking model, to literally all this camera has to do is look for a point of light, because it just shows up as a big, bright white blob in a sea of black. And unfortunately, that did not make it into the demo. It does work, but the conference center would not let us have scaffolding, actually. So we got told no on something pointless but very cool. It's maybe the hackiest thing I've ever done, cutting open a floppy disk to make an IR filter, just because of, I don't know, I guess fire code or something. Killjoys. No fun. But thank you for listening to me ramble about the car update. The technical part of the demo with the like solving an actual real problem was difficult but satisfying. We solved a real problem, and that felt very good, even though we weren't writing production code. Hopefully, if I talk about it enough and rant enough and yell enough on the internet, we will stop building edge devices the way we're building them today and actually consider the consumer's happiness and the longevity of your device, and whether or not you want to be responsible for a big old data breach. Just, the solution already exists. You got to put in the work, but the solution already exists, and it'll be easier after you do it. The fun part of the demo was fun and satisfying, and for $250 or so, you can build this thing too. Don't go for the whole full bore like updates on GCP that we did, but you can build it for $250 and use it to harass your coworkers. We use ours to drive around the office and smash it into the doors of coworkers who are ignoring us on Slack, which is always super fun. You can find me on Twitter at Dixie3Flatline. If you know what that Twitter handle is a reference to, please DM me, because nobody ever gets it and I'm getting really insecure about it. I will send you a JFrog t-shirt. If you go to jfrog.com/show notes, in a couple of hours, my slides will be up there, as well as a whole ton of references, links to all of the open source tools I mentioned, and on and on. I'm also more than happy to share with you the code that we used to make the cool part of the demo work, or answer questions if you decide to build one of these yourself and want to modify it and run into trouble. By the end of this, very, very little of the original donkey library remained on our car, but I'm more than happy to help you modify it or just straight up hand over the code for the race wheel parts and our helm charts and all of that. So thank you for listening to me, and I will take questions now if anybody has any.
Thank you, Kat.
Wow, that was a lot of cool details that I didn't know, like by today. And I do have a question. Can I use my opportunity of the expert and the host to ask the questions, like in the I cut the line and ask the my questions that I personally have. So
okay.
And you see what I'm doing here. I'm not even like waiting until someone will give me permission. So that's why I'm asking this. So, like you mentioned, this the training model took you some time to get some data, train this in either in the cloud on the laptop. Is it something? Maybe it's not the essential part of the demo, so this is why you didn't spend the time to do like a kind of continuous model training type of thing. Is it something that you're considering, or it's not, kind of like a slightly out of scope?
It is definitely something we considered. We wanted to do that. However, we had already been feature creeped so hard that some of our like personal feature creeps had to start getting cut. And that was one of them. Like the green screen was originally feature creep.
You need to have the PM after a certain time so you can prioritize certain features rather than, okay, so let's do this. It obviously, the things around liquid software also resonates in my mind, because I'm all about the streaming data and do the streaming stuff. So this is why how we can replace the ZMQ with Apache Kafka.
The ZMQ was really hacky, but it was that was a product of we had 3 engineers to build this and 3 months. So it was a pretty extreme time crunch, and we were just on what is the literal fastest way we can implement something that will allow us to pass data back and forth in as close to real time as we can get it. Latency was a huge concern because the driver was driving based on the camera feed from the car. So we really couldn't afford more than 100 milliseconds of latency, or people would just crash the car over and over again. So we knew ZMQ was fast and efficient. So we did that first. If we had more time to work on it, I mean, another 6 months to work on it, it would have been a much more sophisticated system.
Yeah, I think it's all about kind of in which place of your optimization chain you are. You're trying to do things faster, and you have some things that are good enough for solving particular task. Once you start looking to the how you can optimize it further, how you can improve such and such components, and this is where some of the more sophisticated tools come into play. And the reason why I'm asking this, we had the similar demo, but it's more kind of offline-ish type of use case where we capture data from telemetry of the it was we used there's open source racing car simulator that actually gives you ability to create very close to reality simulation, so you can get all interesting telemetry about the speed and what's the how fast certain parts of your car are spinning, things like that. So we can process this in order to either provide real-time feedback. For example, if you go into the laps, which part you can optimize, which angle you better attack certain lap, so you save a little bit on fuel, for example, or have a more power to do so. So I think so this is why it's also resonates with me personally. I feel that there's ways where we can collaborate and come up with some interesting things.
Let's do it. I'll resurrect the car demo for that. We still have all the parts.
That's awesome. And I have a question about K3S. what's the requirements for this? Like, if I want to run this, I have a bunch of RP0s lying around my home office, and I want to do something like useful with them. Is it like a right set of tools to try it out on, or like I need to have something a little bit more powerful, maybe RP3s, RP4s, some things like that?
You can absolutely run it on an RP3. We ran it on both an RP3 and a 3B plus. You could definitely run it on a 4 then. It requires 512 megabytes of RAM. I'm not sure how much the Zero has.
Yeah. I think it's
But
512. It's just like a limit. What my zeros have.
I
Michael, are
would
you
try it.
saying something? Yeah. It's exciting. Like the Kubernetes these days is becoming like a Skyrim. Like pretty much like you can run Skyrim
Oh,
on
run it on anything.
everywhere, and you can run the Kubernetes on anything pretty much.
Yeah, it's K3s was much less sophisticated when we did this than it is now. So it was still a little bit of a struggle to get it to run on a Raspberry Pi 3, but it's outstanding. It's so useful. It's so cool. I don't think that everything needs to be Kubernetes, but in this case, it needed to be Kubernetes.
Do you not anticipate, but probably have you faced like a huge roadblocks when you were dealing with different architectures? Like, little segue to our conversation earlier today. Say, for example, I'm running Java, so in this case, I need to use special build of like ARM version of JDK to run my software and things like that. Or if I'm running some of the software that will depend on some native stuff like RocksDB for some storage, that might require some version of libc library available or compiled for ARM and things like that. So what's your recommendation of how to dealing with this, workflow where the people usually deal with like a x86 type of architecture while they developing, and after that they need to move this? Like, what would be developer workflow? What your suggestions, like how to proceed in this type of
So we tried not to we tried not to like cross the streams, so to speak. So we did all of our development for this demo either in Vagrant boxes or on Raspberry Pis. We didn't do any of it on our computers because we just, like I said, we didn't have time. So we didn't have time to potentially deal with issues of architecture. So it was faster to just deal with the extra work of developing directly on a Raspberry Pi or in Vagrant boxes. The only time I've personally had that kind of problem was when I was working with EdgeX Foundry for an earlier project on the IoT team. And it turns out that getting like MongoDB to compile for 32-bit ARM is not fun or easy or supported anymore.
Yeah.
It was ultimately doable, but it was an enormous pain. And I do have like a pretty serious concern about the future of development for Mac OS because of that.
Yeah.
ARM is great. I love ARM. I have friends who work at ARM that are really cool. I love embedded Linux, but maybe it's just bad memories from when I was much younger. And I remember when before Macs were on Intel, a lot of things just straight up didn't exist for Macs. You could not expect to install the same applications. And I was too young to be like writing real code at the time, so I don't know what developing was like for it. But I imagine if nothing existed for Macs, then it was a huge pain. And I hurt for all of my friends who now have to figure out whether or not their tools compile on ARM.
Yeah,
but
hopefully there would be
for ARM.
Huh?
It would be great if
oh yeah, it's good for ARM. Great for ARM. Congratulations to ARM. Like, I'm so proud of y'all. Good job. Get that bag.
No, I think it's great, and the companies like Apple who pushing this, I think they already kind of develop certain expertise and around dealing with this architecture, because like all this, where's this guy, like all these guys, they already running this kind of
they're
like
all
a
on
chips,
ARM,
and
yeah.
they quite powerful in terms of like processing and things like that. But are they powerful enough to do real development workloads? Like, are they powerful enough to do 4K video encoding, editing, and things like that? We'll see. Yeah, hopefully.
I don't know.
Yeah.
There's a developer kit you can rent from them for $500, but the chip in it is 3 years old. So,
Yeah.
and the agreement you sign when you rent the developer test machine from them says you agree explicitly that you won't benchmark the device.
It's funny that you mentioned this, because this is like the conference where the majority of people from the country that loves benchmarks. So like, let's talk about benchmarks and let's talk about performance and kind of things that you already mentioned this, that you didn't maybe do the thorough like benchmarking and find all these bottlenecks. But what would be
Yeah, no, we did not.
kind of like recommendations once we do performance testing? So we going through the test, like a security scanning of the firmware and the software. We're going through the maybe integration test aspect, where we see how the things are working together in this pipeline when we're pushing this device. What about performance? How you would suggest people to look for things like regressions? And it may be general answer, which is fine, but also if there's like some specifics that you've seen some of the projects facing, how different like companies, organizations handle this kind of like regression and performance testing.
I would use Lava. Absolutely, I would use Lava for that, because somebody asked me a similar-ish question at another conference and another version of this talk. He wanted to know how would I know if one device out of 1,000 identical devices failed for whatever reason, because something you got to test in prod sometimes, and something can be weird on just one device. How would you know? The answer is you use Lava to manage all of that for you. Lava's syntax for writing tests is pretty clear. It's pretty explicit. The only hurdle is getting one device type set up. And once you have your one board type configured, you can add 1,000 of those and have Lava make sure that nothing is going to blow up before you actually deploy for real. So you have Lava manage a fleet of test devices and actually deploy your OS, your firmware update or your software update, and have it run through a suite of tests every single time. You're handling your your security scanning and all of that earlier in the pipeline. Hitting Lava should happen right before deployment. If Lava says all of your health checks are green, then go ahead and promote to prod. It is a very, very sophisticated system. It can test virtually whatever you tell it to test.
Nice.
Most devices you have to communicate with it over serial, but it is a pain to set up.
It's really cool. We have like 3 more minutes. I'm not sure if we'll have enough time to answer the question. But when we get into deploying to production, whatever it's mean with 1,000 devices, do you have any suggestion for managing this 1,000 devices fleet, or anything particular you was like from open source? Basically, I already, let's say, have 1,000 device fleet. How I collect data from them, how I collect error rates from them, and all that stuff.
Actually, I think Mender has the option to do that too. I think Mender can do that for you. I would have to double check, but Mender, one of the tools we used, did that as well. It's either, I think it's Mender. Yeah, because it handles the deployment. It'll let you babysit the entire fleet of deployments. So that's what I would just stick with that. That actually might be why we went with Mender over OS3, even though OS3 is a little bit more well established than Mender in over-the-air updates. But yeah, Mender is super, super useful. I'm so glad to see them succeeding. They were much smaller when we first found them, and now the number of like insane logos on their website is bonkers. Good for them. Good job, Mender. You have a cool tool.
And they have
This is what happens when there's a good
professional support.
tool. Yeah, and the good tool is emerging, and the people start using this, and it's. I always saying that it's really cool to work on technology that looks like a magic from the people who are not aware about this technology.
Yeah.
I always say about like Kubernetes type of thing. When you're not like aware how the things are working, but like it looks like magic, like how services go up and down, and nothing is happening. You're not losing data and things like that. But like as an engineer, you also appreciate when everything works, because you know how how the software is. How software is written, and this the statistics that you shared like earlier in your presentation about the bug rate, and I guess it's not like a we need to go where the rate of bugs is like less lower than like 25 bugs per 1,000 line of
Per
code.
thousand.
So.
Per thousand, yeah.
But bugs is fine, but just think think about botnet of your light bulbs
Of
in your phone.
refrigerators.
Yeah, or refrigerators botnet. Yeah, that's cool.
Yeah.
Skynet is coming. And if you want to continue this conversation with us, we have a Zoom link where we can move to our expert zone. I want to say thanks to Kat and Michael to support this conversation. Thanks for awesome talk, Kat. It was amazing. Do not forget to follow her on Twitter. And we'll see you on the next presentation at DevOps. Stay with us.
Thank you, folks. I was really impressed with the talk because it contains of two parts. One is more theoretical and another one is more practical. And I personally like things when I can touch something, when I can engineer something, I can put things together. That's very important to show that you can apply all those data to a physical objects. So thank you so much for being with us tonight. And let's go to the discussion zone, right?
Yeah.
Thank you so much.
See ya.